Yep.
Okay, so we're going live now.
Hello and good afternoon. And let me welcome you all to the workshop number 3 on refreezing the Arctic. And we're going to be looking at marine cloud brightening and other techniques for achieving this. Just a couple of instructions, please. Submit questions at any time using the Zoom Q&A function, please, only the Q&A function. If you want to chat, that's fine, but questions will only be looked at from the Q&A function. And could I also ask that the speakers don't be tempted to reply to the Zoom Q&A, because that tends to lose the question. So I will select from amongst the questions that come in, the questions that I will read out. So you can also ask questions via your YouTube chat or via Twitter, and there I leave the speakers to respond as they wish. This session is being live streamed and recorded, and the recording will be shared on our YouTube channel afterwards. And with that, let me just give you a brief introduction to the Centre for Climate Repair at Cambridge. We have set up the centre, which is focused on 4 objectives, all represented on this slide. First and foremost, we need to reduce, we need to have deep and rapid emissions reduction. Secondly, we need greenhouse gas removal at scale. And that at scale means to bring the greenhouse gas levels in the atmosphere down very significantly from where they are today. And thirdly, repairing the damaged climate systems is referring to the climate systems that have gone past their tipping point, and we believe the Arctic Circle represents the key case of a climate system that has gone past its tipping point, hence this series on dealing with the business of trying to refreeze the Arctic region. We also have a 4th objective, which is really my big focus, to see that there's an agile international political and financial action to deliver all of these processes. We have, I believe, 5 years now to put everything in place and to act on those things we put in place to manage the future of mankind for the next few millennia. The next slide shows us the series that we've just coming to an end with today's meeting. We had a series of meetings on greenhouse gas removal, looking at the ethics and governance, nature-based and hybrid solutions, technological and hybrid solutions. And then climate repair. We began this process of looking at methods of refreezing the Arctic, starting with the state of the Arctic. We then looked at stratospheric aerosol injection and other techniques, and then marine cloud brightening and other techniques today. So I'm delighted to tell you that once again, we have got a superb list of people to give us their views of what needs to be done and what they are themselves doing. And these are the 4 speakers we have today. Professor Peter Wadhams, unfortunately, has fallen ill over the weekend and is unable to be with us, but I'm very pleased to say that our Deputy Director, Hugh Hunt, has stepped into the breach and will give us a lecture on marine cloud brightening, some practical issues that we are currently dealing with. So let me then move on and suggest that we turn to our first invited speaker. And the first invited speaker is Alan Gadian. Oh, yeah, Alan. Alan, I've got your biography in front of me here. You obtained your PhD in the Department of Meteorology, Imperial College, and you're now Professor of Dynamic Meteorology at the University of Leeds. You've co-authored with John Latham more than 10 peer-reviewed publications on modeling the impacts, applying marine cloud brightening to lessen the current rapid global warming caused by greenhouse gas emissions. Alan, could I turn to you to give us a little 15-minute outline of what you've been doing?
Thank you, David. Thank you very much, and for all of you for inviting me to give the opportunity to talk about marine cloud brightening. I've been working on this with John Latham for many years now, and if I could have the first slide, please. Can you? I can't see the first slide.
Yeah, it's coming, Alan.
Oh, it's
1 minute,
fine.
please.
It's fine. Thank you. So the idea is really John Latham's idea, that by injecting sea salt aerosol into marine stratocumulus, we can reduce the albedo, increase the albedo of the planet, and reduce the warming. This idea, it first came out from some work by John Latham, a Nature paper, and it followed on from the work of Slingo, who spent many years looking at marine cloud, the effects of stratocumulus clouds. So here's the first slide. Basically, many contributors, unfortunately, John Latham died recently. Well, I'm just going to give you a brief talk on marine cloud brightening and some of the impacts. Next slide, please, Katie. So there's many of these plots are available. The left-hand one, I don't actually agree with the dates and the timings, but it shows the left-hand panel, what we're looking at. I think probably if we leave it alone, we'll be up to well above 5 degrees C by 2100. If you look at the right-hand upper panel, you can see the latest biomass Arctic sea ice volume, which again shows the danger of the Arctic removal. And we had a very good session on that recently. And finally, the bottom panel shows the latest Stephen Salter's design. Next slide, please. So here, I took part in the Vocals project in 2008. And in the middle panel there, you'll see the stratocumulus, which is over a space of several hours, and the little yellow blob is where there was a ship. So stratocumulus cover 30% of the oceans. Stratocumulus have a high reflectance, which depends on the droplet number and the mean droplet size. And if you look at the right-hand panel, you'll see an example of Stephen Salter's classic example of the difference between having a certain volume of glass beads. On the right-hand glass bead is much whiter than the left-hand set of glass beads, and that is just because of the size of the particles. So let's have a look at this stratocumulus in more detail. Next slide, please. So here is, this came from the paper, the Toomey effect, 1974, he produced this classic paper. On the bottom panel there, we've got fewer large drops, produce a lower albedo. More smaller drops produce a higher albedo. And this came from the Latham 1990 paper. Many people would argue that we've actually been changing the nature of stratocumulus clouds with global warming, but that's a completely separate issue. This is the Toomey effect. This is the basic. Next slide, please. So here is a classic photograph. You might not recognize it, but if you look to the right, you can see the outline of France, the Bay of Biscay, and you have a rectangular box here. And if you look at the optical thickness, that's the bottom left, and look at the effective radius particle size, bottom right, you can see that the most yellow area in the bottom right panel corresponds to the whitest area from the satellite image. And what we have here is a series of ship tracks crossing the ocean and producing the whiter bands. Ship tracks do indicate the effect of marine cloud brightening. The problem is ship tracks are usually various aerosol size, so they can produce lessening of the reflectance later on. Next slide, please. So what are we talking about? Well, for a cloud physicist like me, you can see this Aitken mode, the accumulation mode, And you can see what's sometimes called the Greenfield gap. And this slide comes from Stephen Salter. And this gap here is where a lot of particles are scavenged, and hence there's a dip in the number concentration. And I'm proposing that we should look at inject particles of maybe 200 nanometers size to produce the brightening. The next slide, please. So the first big challenge, and the 2 points from this side, is what is the optimal radius? And this is going to differ depending on the geographical locations. Geographical locations have slightly different structured stratocumulus clouds. And I'm suggesting that we need to have more high resolution numerical simulations to complete this regime. So the current theory, which I think is probably reasonably well represented, is a paper by Elterscar, and I've given a reference for that. Wood has come out with a very recent paper, it's in review, of suggesting a smaller size is optimal. I don't think I agree with that figure at the moment, and I'm going to show you the reasons why in the next slide, please. So this is some work carried out by Mirek Andreychuk, and he worked with, the next slide, please. And he worked with Rayner and several cloud physicists, and he's produced a series of papers. Now, in cloud physics, we have bulk models, we have bin models, and this is a particle model. And I think it's probably the one I prefer. Bin models can be quite diffusive, but we can talk about numerics all day, but that isn't the point. What we did here is just two plots on the left and the right, and they're vertical velocity plots underneath stratocumulus cloud, which has it's about a kilometer, 1,000 meters high. And you can see on the left-hand plot, there's lots more blues and purples. And on the right-hand side, there's lots more greens. So the greens, sorry about the color coding at the top because the yellows haven't come out very well. Greens are small particle size. So we've taken the stratocumulus we observed and we injected, I've only given two, there's low, medium and high, and we injected spray into it. There's a lot in here I could talk about, but all I want to point out is the takeaway message is the right-hand plot where we inject with high, with a high concentration, then you get lots of green. That means it's reflection. Next slide, please. We can represent this in a different way. The two columns there, we've got the left-hand plots. They're the albedo. The right-hand plots, we've got a representation that you saw the same colors as last time, the particle sizes. So let's just take the left-hand plots here. We've got A, B, and C. So we've got high, medium, and low aerosol distribution, and they represent the they represent the sensitivity. So if you look at the top upper left plot, you can see that when there is high aerosol loading in the stratocumulus cloud, seeding doesn't make much difference. So what we've got there is a standard deviation in gray. So it doesn't make much difference. If you look at the lower left-hand plot, where there's lower concentration, you can see that seeding has a significant effect. It increases the albedo by 10% more, 20%. And in there, of course, there's the reference run. So I don't want to go into any details there, but what I'm saying is here we've got the representation of what we showed in the previous pretty picture. If you look down the right-hand side, you can see that the number concentration indeed is much higher in the top case than in the other examples. And the number concentration in the low case, that's the bottom right, is significantly higher. It's more than double the case. So in the low aerosol number cases where you've got a standard stratocumulus, inserting these small aerosol sprays from some source at the surface or wherever produces a significant effect. And next slide, please. All the references are there. So now I'm going to move on to the second part of the modeling, which is the global scale modeling. And again, there's a few references you can look at afterwards. Next slide, please. So This is a technical slide about the details of the HydGem climate model. I think it's useful to put in there. Basically, it's a relatively low resolution, well, in my opinion, but it's considered high resolution. And the model was run, we increased by 1% per year the CO2 to 2045 to double pre-industrial, and then we just let the model run stably from 2070 to 2090. And I'm going to show you some results to look at as examples, the impacts. I'm going to look at the hurricane development, and I'm going to look, which will interest Daniel, some of the work done on the coral bleaching. Next slide, please. So that's a rather technical slide. And this is the two experiments we carried out. If you look at the green blobs, this is the three most populous regions where you get stratocumulus. And that's why they were chosen. They were chosen by Andy Jones, originally with John Latham. So those represent 5% of the maritime surface. They also represent the areas where there's most stratocumulus clouds. The lower right-hand block represents the area where we decided to try and see what would happen if we seeded the whole ocean. However, let's continue on that now. Next slide, please. So here, what areas were seeded for how long? So this is, remember those, if you look at the lower right-hand block, we seeded at 375 per cubic centimeter. And you can see the effect is most strongly noted of minus 40 watts per meter squared over the regions where we seeded the stratocumulus. You can see there are effects globally because we're looking at a global system. The upper right panel is just a brief guideline to remember of what we did up to 2045 CO2 increase, and then let it just settle down. Next slide, please. So this is the first impact, hurricane weakening. So what does it look like? Next slide, please. So here is part of the Atlantic Ocean, and the upper left-hand plot, don't worry too much about the details, is what is the sea surface temperatures between 2 CO2 and 1 CO2. And we get the impression that the sea is going to be a lot warmer. Remember that the intensity of hurricanes depends on the sea surface temperature. When it's above approximately 26.5 degrees Celsius, you get hurricanes. As you get warmer, as Emmanuel showed, you get more intense hurricanes. The bottom right-hand plot there shows what is the effect of when we just seed the three areas. And obviously this area, these two, the area off Namibia and the area off the southwest Southern America, shows the biggest impact there. And the message to take away, all I'm trying to say here is this is an example. You can look at it in the paper, but essentially I've talked about temperature and precipitation in the lower panel. You can see the effect on temperatures. Next slide, please. Next slide, please. So let's now look at the coral bleaching idea that Daniel's going to talk about in a few minutes. So what have we got here? Sorry that the color scale is different. The color scale here is different, but it's the same image. We've got the Gulf of Mexico, we've got the middle of the Pacific, and we've got the oceanic reefs off the three areas that we're looking at, the coral reefs. And you can see that there is significant warming. Now, when we do 2CO2 and MCB, then look, as you can expect, the area of cooling is the strongest over those three areas that we've seeded, but it has an effect on those three regions that we're going to look at. And I'm going to ask for the next slide, because just focus on the bottom slide, which I've repeated. And here we've got some difference. The difference between 2 CO2 and control is of the order of 0.5 degree Celsius. When you put the MCB in those three regions, you can actually reduce it. Now, coral bleaching is rather complicated. It depends on the peaks, not necessarily the warming periods. But anyway, this shows that it has an effect. And you can look at this paper. If we decided to seed all over the globe, then we get a big reduction in temperature. But whether that's feasible or not, I don't think we should do it anyway. But anyway, it shows the effect, a significant cooling of the planet. Next slide, please. So now, what is the atmosphere doing? And this really is, it's driving the system. Next slide, please. And so this is, in fact, my last scientific slide, really. This shows what is the effect. Now, the atmosphere works as a conduit, hot equator, cold pole. So if we look at the red and the blue curves, they're almost on top of each other. And that is the MCB with 3 regions and the control, and they overlap each other completely. If we just do the 2 CO2, the 2 CO2 is the green curve, the upper green curve, and that shows that we're actually transferring heat from the equator to the pole. And this is what's causing, in my opinion, the melting of the ice. If we then globally seeded, then you'd have in the UK, you'd have the ice coming down to the north of Scotland in an ice age. So that's the bottom curve. Next slide, please. So this is the final idea is coding manipulation, which, next slide, please, Stephen Salters. So if we divide, no, the previous slide, thank you. Upper right plot is we divided the globe into 89 sections. We turned the seeding off for 10 days. We thought 2 days was too short. 10 days was about right. And the bottom right shows that some areas have bigger effect than other areas, which we expected. We expected Namibia and the Southwest Pacific. Next slide, please. So here, this is the last picture I'm going to show, shows that if we take 2 regions, just consider precipitation, the northern Amazon and the southern Amazon's on the left, what areas would affect the precipitation in those regions the most? And this is the seeding pattern. In fact, it increased rainfall overall in southern Amazon. If we looked at the northern Amazon, the right-hand picture, you can see there's some blue blobs where seeding would reduce the Amazon precipitation. This idea of where you could seed what is the impact on certain regions can be investigated and to try and minimize side effects. Next slide, please. So what have I done in the talk? This is a summary. I've presented some background information on marine cloud brightening. I've presented some papers, I'm afraid mainly mine, but there's a lot more out there. I've showed some high resolution model simulations, and I've represented some results and impacts of the global climate model simulations. And finally, that coding manipulation could be used to try and minimize side effects, because there will be side effects. However, the side effects are will minimize also the huge effect that double CO2 will have on precipitation over the globe. Conclusions: need to optimize the size of the CCN, and we need more simulations. Thank you very much, David. Thank you very much, Katie.
Can you hear me? Right, so basically I've got a couple of questions have come in, and the first thing is to emphasize that everything you've presented to us is modeling, and so I just have my own little question: the reliability of models. Do you have checks on reliability?
I use models all the time, and I find them very unreliable. I think we should, and I think Brian Hoskins would agree with that, who is also a modeler. I've now done some work with 2 kilometer modeling, and I think that's much better, which shows that, but the idea is, I think in principle, the models are quite good. I think they're very good for temperature, surprisingly. I don't think they're very good for precipitation. The models need to be improving, but so far the models have been reasonable. They've been predicting the right sort of trend. The models of ice destruction have been catastrophically bad. So the loss of the Arctic ice was predicted. If you look at all the ICCP reports, they totally underestimate it. And I've talked with people at ECMWF about it, and they agree that even their daily forecast models that ice. So for the numerics and the modeling, for the global scales, inadequate, but I think they have the right trends.
Thank you very much. I've got a question from Hans van der Loo, who says, is minus 0.04 degrees centigrade to minus 0.58 degrees centigrade, taken from your modeling, enough to make a material difference to impact Arctic melting?
I showed the picture of the meridional heat transfer, and that is, so you've got numerous papers, Julius Lingo, lots of papers. That is the critical role of the atmosphere, is to move heat from the equator to the pole. So you might be dealing with small temperatures, but the amount of advection is huge. So the oceanic transport is very slow. It's the atmospheric transport. And I think that all the results, they're consistent, that even such small temperature differences in the air mass, of course, the latent heat release is phenomenally important. One could argue that the Greenland is being heated up by latent heat release of energy. There's lots more moisture there than the temperature. I'm not going to argue with that or one way or another, but the temperature is a guide. Latent heat and moisture fluxes are huge with meandering jet streams. They're taking all this warm, moist air to the Arctic.
Alan, thank you very much. I'm going to ask you to stay in for the Q&A that will follow all 4 speakers. And now turn to Dr. Daniel Harrison. Daniel is a senior lecturer in the Faculty of Science and Engineering at Southern Cross University, Australia. He completed his Bachelor of Engineering, Civil, Masters in Engineering, Oceanography, and PhD, Biological Oceanography at the University of Sydney. And he is a visiting scholar. He was a visiting scholar at the University of Southern California, where he helped to develop tools to improve the use of oceanographic data in ecosystem-based management of fisheries resources. He, in 2017, was awarded a prestigious Maya Innovation Fellowship to develop the concept of using solar radiation management approaches for bleaching protection on the Great Barrier Reef in 2019. Daniel joined Southern Cross University as senior lecturer and was appointed sub-program lead of the cooling and shading sub-program within the Reef Restoration and Adaptation Program. And it's this work that Dan is going to give us a talk on. Dan, over to you.
Thank you, David, for that very detailed introduction. I'll just share the screen here and hopefully all goes well. Oops. Oh, it did, except I wasn't at the start of the show. There we go. Got a very quick preview there in backwards order. Okay, so thank you very much for this. This work I'm going to present is obviously been contributed to a lot of people besides myself. We've been working on this now for a few years, since that fellowship in 2017, really. And one thing I just really wanted to say at the outset of this talk is that it's far too much work to summarize in 15 minutes. So I've had to make the decision to really focus on the technical aspects for this talk. We're doing a lot of work into everything from social science to working with traditional owners about these technologies to incorporate their views into the research program, right through to looking at environmental risks and all of those kind of things. But necessarily I've had to make this short, and I've chosen to focus on the technical aspects. So, as you're probably well aware, the Great Barrier Reef has really been suffering the last few years. In the last 5 years, we've had 3 mass bleaching events, which is completely unheard of before. So we had on the Great Barrier Reef some previous bleaching events, quite minor, associated with El Nino years back in 1998 and 2004, but fairly minor localized bleaching events. These last three events, which have come almost back to back, in 2016, 2017, were back to back. Over that time, as you can see in this slide, we've had nearly the whole reef affected. That's over 2,000 kilometers from the north to the south. And in fact, it would be a lot worse, except that during two of those bleaching events, cyclones actually came and mixed up cold water and increased cloud cover and helped to reduce some of the severity. But even with that stroke of luck in some sense, although the cyclones also cause a lot of damage when they do impact directly, and associated die-offs of the coral. And so if we look to the future, this is just a plot of the global mean surface temperature of the world. And of course, we all know it's been rising since the Industrial Revolution and the associated greenhouse gas emissions. I've marked on there in orange the two relatively minor bleaching events, historic, and the three mass bleaching events there in red arrows that we've had recently. And if we just take a very, very simple linear fit to this curve, which you can see there with the green dashed line, and we predict that forward, those bleaching events occurred during slightly anomalously high global temperatures, mostly associated with the El Nino cycle. But in 10 years' time, those high temperatures that we experienced briefly will be the global average temperature. And if we have an El Nino event in 10 years' time, it might look something like that. If we push that out to the optimistic goal of Paris of a 1.5 degree temperature increase globally, and then we had an El Nino event, it might look like that. We go all the way out to 2 degrees, which is, I'd argue, still quite optimistic. That's where we are. And so you don't need a complicated model, I don't think, although we do have some, and I'll show you some results from some later, complex ecological models of the Great Barrier Reef. But in my opinion, this simple plot here tells the story of the future of the Great Barrier Reef. Without intervention, and even with really strong action on carbon emissions now, the reef's still going to be in a lot of trouble. But a hint of what might be possible in terms of cloud brightening comes from this somewhat older modeling paper here, where the authors looked at the sensitivity globally of clouds to marine cloud brightening. And while they didn't necessarily find that the most sensitive clouds or the very best clouds for cloud brightening were present over the reef, this particular plot shows the net average global forcing from cloud brightening applied over all of the world's oceans. So a scenario that Alan talked about earlier, but didn't necessarily show us the results from. He concentrated on results where just the best regions were seeded. And the interesting thing about this plot is that the Great Barrier Reef there in the northeastern side of Australia actually happens to be in one of the areas that responded in terms of radiative forcing quite well to this sort of uniform imposition of cloud brightening. And so that was one of the very early bits of evidence, I think, that I found that cloud brightening could potentially be useful over the reef. And so if we look at this a little bit more closely, what evidence, what prerequisites, I should say, do we need for cloud brightening to potentially be useful over the reef? Well, we need clouds. The concept of cloud brightening requires clouds to alter. It's not making new clouds, which is an important aspect to understand. And because we're seeking to alter clouds which have a net negative radiative forcing on the Earth, a cooling effect, and also because we hope to reach these clouds by introducing particles to the planetary boundary layer, we need low boundary layer associated cloud. And for those clouds to have the potential to respond to cloud brightening, to these extra cloud condensation nuclei that we're going to feed them, we need there to be low existing background concentrations of cloud condensation nuclei. As the concentration of cloud droplets go up, the potential for increasing the albedo decreases exponentially. So the first 100 extra cloud particles you can create or cloud droplet concentration you can create gives you the most albedo increase. The next 100, only half that or something. The next 100 after that, a quarter. So if there's already reasonable background concentrations of CCN particles, it's very hard to make a difference. And the final thing that we need for this to work on the reef is we need, because we're considering here not a very large scale continuous application of cloud brightening, what we're actually looking in these scenarios I'll present is a reactive cloud brightening. So a limited area just immediately over the top of the Great Barrier Reef, some 0.7% of the Earth's surface, for a limited amount of time in response to an acute heating event, such as a marine heat wave, which has caused these mass bleaching events. So the idea here is not large scale continuous cloud brightening, but quick and agile reactive cloud brightening for probably a period of a few months or so over one of those marine heat waves to try and relieve the stress on the coral reef. And so for that to work, that sort of limited application in both sort of spatial area and also in time, you need the hydrodynamics to also be compatible. So we happen to have that on the reef because the reef is quite shallow and the water has a fairly high residence time there. So it gives us the opportunity to potentially cool it down in a limited amount of time. Or rather, I should say more accurately, to prevent it heating up as much as it otherwise would have. And so if we just quickly go through a few of these prerequisites, some analysis shows that actually, despite what a lot of people probably first thought, there is a fair bit of low cloud fraction over the Great Barrier Reef, and even during an El Nino year where there's substantially less than normal, these 4 plots or 8 plots divided into 2 years are over those 2 mass bleaching events that we've modeled so far. And you can see that although in some cases, like February in 2016 there was very low cloud cover over parts of the reef, and that is associated with that mass bleaching event because corals bleach from both from being too warm in the presence of high light energy. So you can help to prevent coral bleaching either by lowering the amount of light energy or lowering the temperature. And of course, cloud brightening has the potential to do a bit of both. And also, if you look at the global model there in the top right corner, that also predicts a reasonable fraction of low cloud cover over the reef. Next, the existing concentration of cloud condensation nuclei. It's quite fortuitous for this idea that during summer, when the coral is at risk of bleaching, the trade winds bring quite very clean air from quite remote areas of the subtropical South Pacific in over the reef predominantly. And that air happens to have some of the lowest background cloud condensation nuclei concentrations anywhere on the world, sort of outside of the poles. And this translates to low droplet concentrations, background concentrations in the clouds over the reef, which are shown in those right panels from satellite retrievals. So the key questions then for the technical feasibility of cloud brightening, given that we think most or maybe all of the prerequisites have been met, are the clouds over the GBR then, are they actually susceptible to these extra cloud condensation nuclei? The prerequisites are met, so we believe that they should be susceptible, but are they, and what is their sensitivity? What cloud condensation nuclei sizes are effective and what are detrimental? We know that if we have some particles introduced that are too large, they could help encourage precipitation and have the opposite effect. And it may be the case also that if they're too small, under certain circumstances, they may also have the opposite effect. And so once we do know what size that we need, can we produce them in sufficient quantities? We need to produce really immense quantities, very, very small, so small amounts of mass, but immense numbers of these cloud condensation nuclei to be able to have any meaningful impact. And we'll talk a little bit more about that later. Next, what is the envelope of cooling and shading that can be achieved? And is it enough to provide benefit? So the clouds over the reef are not the ideal clouds for marine cloud brightening. They're not large, persistent decks of marine stratocumulus clouds in general. There is some stratocumulus clouds, but there's more trade cumulus, which are less ideal for cloud brightening. But in the case of trying to prevent corals bleaching, we don't necessarily need the very, very best clouds in the world. What we need are clouds that are good enough to have an impact that is enough to help preserve the Great Barrier Reef. And then given that, what are some realistic engineering design assumptions around nozzle performance and the energy requirements? So even if we can create enough cloud condensation nuclei in a sort of a single station, if you'd like, how much energy does that require, and is it reasonable to scale that up to be large enough to do an area as big as the Great Barrier Reef, which is some 350,000 or so kilometers squared? Very large area, even though it's a very small fraction of the Earth. And so we'll move on now to looking at addressing some of those technical questions. And the next part of the talk is just looking at some of the things we've done in sort of preliminary work to start to address these questions. And this is some preliminary, fairly high resolution cloud microphysical modeling to get a first impression of whether the clouds over the reef are in fact sensitive to additional CCN during the period that we're interested in. And the results from this suggested that an albedo increase of up to around 0.3 from just considering the Toomey effect alone, not including also the potential direct effect of the aerosols themselves, and also not including any potential second indirect effects of cloud brightening, such as increased cloud lifetime due to decreased precipitation and other second order impacts. And so that was quite encouraging, but it is quite preliminary modeling, and that's published for those that want to have a closer look. And so next we move to the hydrodynamic modeling. Okay, so if we can get an albedo increase in the clouds, does that translate to an actual cooling of the ocean, or is there simply too much water moving too quickly to cool? And so for this, we're quite lucky because the CSIRO in Australia has spent many years with partners developing a very, very accurate hydrodynamic model of the Great Barrier Reef, which also has within it a biogeochemical model and even a coral bleaching model, which I'll show some results of later. But the point here is that it gets the hydrodynamics very, very right. The root mean square error on the water temperature is less than a degree, I believe. I think 0.3 from memory. And so on the right there, it's just a few of the scenarios we run, but actually, sorry, on the left actually shows a scenario of 0.3 albedo change to just the low cloud fraction during the 2015-2016 year. So the actual conditions that bleaching occurs under. And like Alan found, it's interesting that, and this was a bit of a surprise to us, that the cooling is so isolated to under the cloud that's impacted. We expected that the water movement would sort of advect that cooling influence a lot further, but the direct cooling is really shown to be quite, and so that result there is actually also quite representative of the spatial distribution of the forcing. Although what we do see, of course, and you can see it in the right panel there as well, where the results are plotted for each individual reef within the GBR ecosystem, that as you move from the edge of the shelf in towards the coast, the amount of cooling that's achieved increases, and that, of course, is because the residence time of the water under the changed cloud increases as you move away from the edge of the area that you're influencing. And so we can summarize those results in this plot from a whole bunch of different scenarios. And I guess that without talking about this too much, the main takeaway point here is that using, I think, perhaps optimistic but reasonable assumptions, we can probably achieve something like 0.6 or 0.7 of a degree change in temperature of the surface ocean across the GBR. Well, not all of across. This is sort of an average mid-shelf. And what we also discovered by changing the scale of the area that we were conducting cloud brightening, if you go out to that whole model domain, so well out into the Pacific Ocean, you can get an extra 20% or so of cooling. And if you sorry, an extra 40%. And if you reduce the area down to only about a quarter or so of the GBR, you lose some efficiency, about 20%, but you still get about 0.5 degree cooling under that particular scenario. If we then move to the biogeochemical component of that model to look at the coral bleaching, what we find is quite interesting. Because we're reducing both the light and the temperature, we're able to reduce a lot of the stress in the corals. And because the biogeochemical model can only be run in a nested configuration at a very high resolution, we had to do this for a representative sample of reefs, not all of them, many more than are shown on this slide though. And what we found was that with the lower cloud cover during 2015, 2016, we were able to reduce the bleaching stress by about 50%. And that was because that was such a strong El Nino year. In 2016, 2017, that was about 65%. We haven't yet been able to take the step to translate that to mortality, but we suspect it's very high because the mortality is sort of results from peak stress. So by reducing the stress by 65%, we think that you reduce nearly all of the mortality. And if you then take those results and you put them in ecological models that have been used to predict the future of the reef, I'll just spend a little bit of time on these slides, but if you look at the two panels in the middle there, the dashed line there is the same in both, and that's the future prediction of the reef without intervention. And of course, it's not the same because the top one is a Paris-type climate scenario, and the bottom is a more business as usual type scenario. And but you see in both that the reef goes through a period of decline, and if we meet Paris, it levels off with some coral cover remaining. The y-axis there is fraction coral cover on the reef. Although in a business as usual representative concentration pathway of 8.5 watts forcing, we lose the reef completely. And then the solid line, of course, is with the cloud brightening intervention. And this is a really, really important result, I think, because if we have a Paris-type commitment to climate change and emissions reductions, and we also do cloud brightening, this model result shows that it's possible to have the reef bounce back to its previous levels, at recent levels of health, and to sustain that at least out to 2075, which was the model run. However, if we don't have really, really strong action on emissions, then the cloud brightening essentially delays the degradation of the reef by a couple of decades, but eventually there's only so much scope for brightening the clouds. You can't just keep adding more particles and getting more cloud brightening. So you eventually run out of scope and simply you're overcome by global warming. Another interesting finding of this modeling was when we combined interventions, so not just cloud brightening, but some of the other interventions that the Reef Restoration Adaptation Program is looking into, they nearly all synergized very, very well with cloud brightening. So helping to relieve some of that stress helps you with other restoration and preservation interventions that you might make on the reef. The last part of the talk is just looking at some of our results from recent field studies. So we've been out to the reef twice now, testing a cloud brightening prototype, which is not so much a real prototype, but rather a test rig, I'd like to call it. And the idea here has been so far not to influence the clouds, but to start to look at some of those engineering type questions which you can't answer in the lab. So there's been probably a decade or more of work prior to this time working on nozzle development in the lab, both by others and also by ourselves at the University of Sydney, this work was. But now at the University of Southern California, we've been fortunate enough to get enough funding to take this idea out into the field with the support of the traditional owners who own these waters. We don't do any work in the field without the free, prior and informed consent of the traditional owners that have historical access rights over that area of the Great Barrier Reef. And also obviously with the permissions of the regulators, which in this case is the Great Barrier Reef Marine Park Authority. So the research here is very highly regulated, and of course there's a permitting process to go through first.
And could you try and wind up in about 2 minutes?
Yep, sure. by probably going fast. And so this is just a bit of a schematic about how we've been doing some of the field work. But here are some results that will probably interest some. So in our most recent experiment, we were producing around 3 × 10⁻14 particles per second, with the size distributions shown there on the left. An important point here, I think, is that if we take Rob Wood's recent prediction of a good sort of effective size range for cloud brightening, that's the yellow shading, and a sort of perhaps more restricted representation of the more ideal size, perhaps there, the larger and more narrow sizes there in the green shading. So currently the size distribution fits quite well, at least for 2020. We tried new nozzles this last year to try and push the size distribution larger, but it actually just broadened the size distribution, so it didn't live up to expectations. And this result shows the results from our drone flying back and forth during the plume. And the takeaway message here was that we were worried that the evaporative cooling of the evaporating seawater may cause the plume to sink and flow across the ocean, at least in some atmospheric conditions. But we've now tested across a wide range of atmospheric conditions. And in fact, there seems to, in the summer, due to the very hot ocean, be generally quite an unstable atmosphere and very good vertical mixing of the plume. So the final slide here, I'll just put all of them up there. But essentially what we've found so far is that 10 to 20 watts per meter squared average reduction over the summer is enough to alter the trajectory of the reef. Ecological modeling showed just 0.3 of a degree reduction in ocean surface temperature is enough to alter the trajectory of the reef. The evidence continues to suggest that the clouds over the reef do appear to be susceptible to cloud brightening. The plume is well mixed vertically, and so our results so far have suggested that our particles reach the cloud base in only around 4 to 6 kilometers downwind, generally. Size distribution's not yet ideal. We think that we need more like the historical assumptions around size for the clouds over the reef for technical reasons I don't have time to get into. And finally, that we're very close to being able to produce enough sea salt aerosols in an experimental sense to begin to look at their influence on the cloud microphysical properties. And of course, the really critical result there that this research isn't going to be useful in terms of helping the reef unless we also have strong reduction of emissions. Thank you.
Thank you very much, Dan. Could I just give you a question that's come in from John Nairn? Is cloud brightening assuming a very evenly distributed effect? Does it rely upon stratiform cloud versus cumuliform cloud? And if uneven, he wonders whether the seeding may change stratiform cloud into more cumuliform fields with potentially strong penetration between clouds.
The last point's an interesting one, which I haven't considered too closely, and would be one for the more true cloud microphysicists rather than the oceanographers like myself. What I can say about the uniformity, though, is that interesting. Some of those scenarios I showed that resulted in that nearly linear relationship between average forcing and sea surface cooling were uniform forcing fields, so sort of in a sense representative of direct forcing, sky brightening, perhaps, rather than cloud brightening. And the result there was that between the movement of the clouds and the mixing of the ocean, it made essentially no difference whether the forcing was applied just to the low clouds or was applied evenly over the same area. The ocean cooling was essentially the same for a given amount of average forcing. But the second question I'd have to take on notice and consult with the cloud microphysicists.
Dan, thanks very much. I've got a bunch of questions coming in, but we'll hold them for the general discussion. I do have a comment, which is that you're saying, of course, we need deep and rapid emissions reduction, even if you continue with your work to try to manage the Great Barrier Reef. But of course, we would say reduction isn't enough. We need to remove greenhouse gases that are already in the atmosphere to get ourselves back to the position where, for example, the Great Barrier Reef doesn't need these continued interventions. But let me just say thank you very much for a very clear presentation. Now, the next presentation is from Dr. Leslie Field. And Dr. Leslie Field is the founder and chief technical officer of the Arctic Ice Project, a lecturer at Stanford University, and the founder of Small Tech Consulting LLC. Her work includes Arctic ice restoration, teaching at Stanford, and consulting in the area of microelectromechanical systems and nanotechnology. Now, Leslie is not available to us at the moment, but we have a pre-recording of her speech. So I'm going to pass this over to my colleagues to see that you now are exposed to the pre-recording. Thank you.
Hello, I'm Dr. Leslie Field, and I am so honored to be a part of this impactful series of workshops. I'm disappointed not to be able to be there live during the discussion section especially. Please send any questions to me at lfield@arcticiceproject.org, and I'd love to have a conversation with you later. Why am I not able to be there? Original date I could have, but as it is with the change needed in the schedule, I'm already locked into a backpacking permits in the Rocky Mountains with my son, our youngest son, Gregory. And those are not arrangements that can easily be changed. So my apologies. Think of me in the mountains. Just delighted to be here. And I'm very happy to be speaking about localized albedo modification, localized surface albedo modification for ice preservation and regeneration. Thank you. You've probably seen movies like this, and I hope you've been discussing this to some extent already as well. But in case this is your first that you're looking at during this seminar series, the idea about Arctic ice, why it's so important to climate change, is that it has been disappearing rapidly in a positive feedback loop over the last just several decades. So here, month by month, you can see, as Professor Don Perovich calls it, the beating heart, the breath of Arctic ice as it's melting and refreezing over time. What's happening, though, is that sea ice over 4 years old is brighter, right? You can see the brightness that they're reporting is brighter as ice ages. And the inventory of sea ice over 4 years old is disappearing, is reducing over these years. And so it's not just temperature rise, although that's a good deal of it, warming ocean, rising temperatures atmospherically as well. It's ice export as well. Things have changed a lot. And so as we lose this bright reflective ice, we're losing the planet's historic icy heat shield in the Arctic that used to fend off much of the 24-hour per day sunlight in the Arctic in the summer. And that's a big deal. That has added our heat load to the planet and is accelerating global temperature rise enormously. And you can see this isn't just some short-term weather variation. Over the course of these decades, it's gotten more and more rapid, and it really looks like there is no natural way back to have the ice reappear if we just do nothing. If we pull down CO2, if we pull down greenhouse gases, if we can cool things a bit, then yes, ice could very likely come back. We're lucky enough to keep reforming it every winter, but it's young, thin ice that doesn't reflect much increasingly. And so this is a devastating impact on our planetary systems. So the loss of older ice means loss of brightness, loss of albedo. And as Professor Peter Wadhams has said in his beautiful book, A Farewell to Ice, this overall change in the Arctic, adding land ice and sea ice together, can add as much as 50%, accelerate by 50% to the direct global heating effect that we've already got in the atmosphere of CO2. Dr. Don Perovich, another wonderful ice expert, says that back in March of 1985, old ice comprised about 30% of Arctic sea ice cover. Now, a couple of years ago, as he was addressing the American Geophysical Union meeting, delivering the NOAA report card for that year, a couple of years ago, now it's about 1%. So we've really lost enormously beautiful reflectivity that we've historically had in the Arctic. There are a lot of considerations if you want to do something about that, though. And I, as a sort of terminal technologist, you know, the first reaction is let's make a technical solution. And that's true, we need technical solutions. But we also need to consider the whole framework. And I really love what our colleague, Dr. Danielle Chamberlain at Arctic Ice Project had put together, just showing some of the stakeholders and some of the considerations we really need to include if we're going to start considering doing any climate interventional solutions. I've been passionate about trying to make sure that we understand and, if necessary, help form the policy and governance discussions and decisions that will allow people to understand who can impartially evaluate what is actually in the best interests of humanity. And we have to consider everything, especially the people who actually live in the regions that we're thinking about doing interventions in. This is a picture of us with some of our crew up in Utqiagvik, Barrow, Alaska, where we've done a great deal of testing over the years. So these framework considerations are key. Here it is in a little larger format for you. And we have a proposed solution that's been working into that framework from the beginning. From the beginning, I have known that first do no harm was going to be my most important principle. If we're going to make an intervention, then for Pete's sake, let's make sure that it doesn't harm something, that we could undo it if we needed, that it's not harmful in the first place. After many years of testing many materials in various locations, our favorite choice is silica glass, hollow glass microspheres, and these are commercially available. That's very key. You want to make sure you don't have to bring up a new manufacturing process in order to do this. This is a close-up of the spheres. This is what they look like in a little jar. They basically look like a foot-friendly sand, white floating sand. And they are used widely in many, many applications right now. There's a number of these properties that are very deliberate. I didn't want anything to be able to bind with oil-based pollutants. Hydrophilic is really great. Once we distribute them, they cling to the ice or water because they want to stay there. They'll blow around with waves after a melt, but they stay. And it's one of silica, the major component of these hollow shell, forming a hollow shell around a gas sphere that reflects away sunlight. Silica is one of the most abundant materials on the planet, so we've all evolved with it. And it's very prevalent in marine and land ecosystems. And it's very different than plastic. It's passed all the safety tests so far, but we're continuing to test. We're raising money to collaborate with marine biologists who can help look at some of the more subtle aspects of this that are going to be very important. And basically, a thin coating takes us from that open ocean, almost no reflectivity of incoming sunlight, and beyond the thin ice, measurements that actually Don Perovich's group has done many, many ice albedo measurements. It'll pull us beyond that to instantly boost the reflectivity of young, thin ice towards what one could have with very old ice, especially with a snow cover. And over time, if we can preserve this over a melt season, we then form the base layer on which the next season's ice can grow, and we start to be able to reboot multi-year ice. We're looking for that. We're looking for the right locations where that could happen. We've done controlled tests for years in collaboration always with the local residents. Here's somebody from UIC Science up in Utqiagvik, Corey, with an instrumentation volunteer who's worked with us on and off for many, many years, Satish. And so this is in Utqiagvik, drilling an ice core, of course. And here's a pond in Minnesota where we have a mighty team of volunteers in a backyard pond. And here's the materials put out on, square by square, so we get even dosing on a treated section of the pond, and here's untreated control. so that we can study what's going on. Here's that same pond, different year, this year, with bare ice and then treated with hollow glass microspheres. And you can see it's an instant boost in reflectivity. This really bright area, of course, is snow. You can't beat snow. But snow is not a problem for these. If snow falls on top, so much the better. Once it melts, we find that the hollow glass microspheres are very effective on meltwater. This year we had the best, most solid, most data-rich data set we've ever had on a test pond in Minnesota. It was real-time reporting here in California from the pond in Minnesota. And this is just a sample of the kinds of things that we were measuring. Here's some drone footage we had from overhead right after application and then into the melt. You can see we segmented the pond with a thin pipe, actually. And we've done ice melt comparison with a sequence of drone footage and these measurements. The data reduction is still in progress, so we're not quoting the numbers quite yet, but we will publish a scientific paper promptly when the analysis is complete. But what we got to see was the starring thing was that as soon as all the snow had melted, then the HGMs are really taking on their role to increase reflectivity over what the underlying ice was. And so floating on top of the melt pond. So that's terrific. And this lets us be bold enough to say that we could probably help with glacial ice as well. And that's huge because we have crises in Greenland and the Himalayas, at risk the drinking water for over 1 billion people from Himalayan ice melt, and global sea level rise threatening all coastal communities if all of Greenland went. And so we'll continue to say that the HDMs, we have data, we have quantification coming on how effective they are on melt ponds. And so far, everything looks safe, but we are going to continue to test, and make sure that this really is safe. If not, we're Silicon Valley. We can pivot a material if we need to. We have many people on our, well, most of our technical team is expert in materials, and we can make the pivot if we have to. We do climate modeling through partnership with Climeformatics, a mighty team of experts here. And we've been modeling with them, they've been doing the modeling, a couple of strategic areas in the Arctic that might allow us for leveraged deployment. That is something that will have beneficial effects beyond the small area that we intend to treat. And that's a very key thing. The indications all are that we don't need to carpet the Arctic. There's a lot more modeling needed in order to get this all vetted out. Of course, the cost of doing nothing is huge, and the impacts are devastating. This is a NOAA, National Oceanic and Atmospheric Administration, map of the impacts in just one country, the US, in just 1 year, 2018, where the costs were almost $100 billion. And of course, the climate's getting less stable, so the impacts are getting worse and worse. To not do anything is really, it's unconscionable. It's not in the best interest of humanity, that's for sure. On the other hand, we do want to make sure that interventions that are made, proposed, and then eventually funded and implemented are going to be ones that are actually in the service of the best interests of all of us. And so restoring polar ice, this tragic outcome, the loss, the melt, is a tragic outcome of global temperature rise, but restoring it is a crucial lever that could slow climate risks and harms while the world urgently decarbonizes. I mean, why not just do that? It takes time. It takes time to turn over the infrastructure. These sorts of interventions are a band-aid, a temporary help to slow that global temperature rise and global climate devastation down while we get to do job one, which is that urgent decarbonization. And this is the time to act. It is almost too late to be able to prevent these enormous harms. We're building collaborations to accelerate the work. I would welcome collaborating with you. And again, please write me if you have questions or want to follow up, lfield@arcticiceproject.org. Thank you so much. Take care. Bye-bye.
Of course, we don't have Leslie with us to answer the question, but it's a good one. It comes from Hans van der Loo, and it's been upvoted by quite a few other people. Can the hollow glass microspheres, the silica, enter the food chain in the way that plastic is doing, or do its characteristics mean it would not be digested and leave any body unchanged? I think that is a question that must be on Leslie's menu of things to be done in terms of her experimentation, and it's certainly a question that we will pass on to her. I'm now going to move straight on to our last speaker of the day, our own Dr. Hugh Hunt, who is Deputy Director of the Centre for Climate Repair here and a reader in the Department of Engineering at Cambridge University. He is also a Fellow of Trinity College here in Cambridge. He stepped in to talk today at less than 24 hours notice, very keen that I should let you know that. His most recent research is in the fields of renewable energy and geoengineering, including the SPICE project. He took his first degree in engineering from Melbourne University, I think you'll tell from his accent, in Australia, and has a PhD from Cambridge University. He is going to give us a talk, I think, on marine cloud brightening and describe the experimental work underway at Cambridge and Edinburgh, and of course working alongside Alan Gadian at Leeds. Over to you, Hugh.
Well, thank you very much, Dave. Yes, hopefully I can do my best to do some justice to this topic in this afternoon's presentation. It's been really interesting to hear the earlier speakers. I grew up in Australia, and really, you take the Great Barrier Reef for granted. It's a beautiful place, and it's threatened. And we're in a position now to be able to do something about it and about other threatened parts of our planet. And now let me just share my screen here, which I think I can do. Hopefully you can see that. So the Arctic in particular is threatened. We've heard about Arctic amplification. Yes, the world is warming, but the Arctic is warming faster. And we've got to come up with techniques to try to manage this warming. Yes, we've got to stop emitting CO2 and methane and other greenhouse gases. We've got to stop burning fossil fuels. That's number one, as we've heard several times today. We've also got to try and get carbon dioxide and methane out of the atmosphere, the stuff that we've already put in there. But what we're talking about today is ways of reflecting sunlight. And now, solar radiation management, as it's called, I don't like that name. Management suggests that we're in control of things, but solar radiation management comes in all sorts of different forms. And you might have come across some of these forms with perhaps reflecting sunlight by making the oceans more foamy. That's been talked about. Perhaps increasing the reflectivity of the land. Perhaps we can use genetic modification of crops to make them more reflective. We've heard a bit just now of increasing reflectivity in polar regions. Perhaps we can increase reflectivity of deserts. But there are two that are particularly interesting. There's increasing reflectivity from clouds and increasing reflectivity in the stratosphere. And so marine cloud brightening is this increasing reflectivity from low clouds, and stratospheric aerosol injection we heard about on Monday is increasing reflectivity high in the atmosphere. Now, a question that was asked on Monday is whether marine cloud brightening, is it possible that marine cloud brightening could be as effective as stratospheric aerosols? So I just quickly want to sum up in one slide the stratospheric aerosol idea, which is that, well, we know back in 1991 that Mount Pinatubo put about 10 million tons of sulfur dioxide up above 20 kilometers. And if we wanted to achieve, say, a 2-degree per year cooling, question mark, is that what we'd be interested in? We'd need about 2 Pinaturbos, let's say, per year. And based on what we know from Mount Pinatubo, we've got a reasonable estimate that means putting 55,000 tons per day of sulfur dioxide up into the stratosphere. Now, to do that, we'd need, with 10-ton payload aircraft, can we do it? 5,500 flights per day, which sounds completely nuts. And it is completely nuts. But I just want you to bear that figure in mind, because it'll come back again. 55,000 tons a day of sulfur dioxide, which, by the way, compare that with the 100 million tons per day that we on this planet generate in CO2. I mean, I think it's crazy that we start being nervous about figures like 55,000 tons a day, but this figure we kind of just brush off. Anyway, that's another point for another day. So what if we were to do marine cloud brightening? And I've tried to kind of pick up on comments that have been made before. If we're going to spray seawater into clouds to increase reflectivity, well, let's try and do some sums. And I'm grateful very much to Stephen Salter, who's done quite a few of these sums to keep us on our toes. We're trying to increase reflectivity, and he's been suggesting that, well, if we could increase the number of cloud nuclei to maybe by 50%, then that'll increase the amount of clouds. He suggested that to do this, we'd need maybe 100 spraying ships, each generating 10 to the 17 saltwater droplets per second. Well, Daniel was talking about these amazing numbers, big numbers. We're just trying to get a handle on this. 10 to the 17 saltwater droplets per second. These saltwater droplets need to be 0.8 micron, 800 nanometers in diameter, to produce 200 nanometer salt particles, these cloud concentration nuclei. We've heard about them earlier. Now that translates to 230,000 tons of water per day. So compare that figure with the 50,000 tons of sulfur dioxide. You kind of think, I'd much rather be spraying seawater, even if we have to spray more of it, than sulfur dioxide. It feels right. So what's really imperative is that if this technology can work on this sort of scale, then we've really got to work out, can we do it? And this then becomes an engineering problem. And yes, of course, there's all sorts of climate modeling stuff required. There's no doubt about that. Now, the climate modeling, there is some variability. If you look at these various pictures which come from, I mentioned at the bottom here, Camilla Stern's Marine Cloud Brightening research at the Cicero Lab. This is from a couple of years ago. There is a lot of difficulty in being sure about how clouds work. Clouds are really tricky to model. Now, what we're doing in our Centre for Climate Repair is to do modeling of the climate and of clouds to try to be sure that the anticipated effectiveness of marine cloud brightening can be realized without unacceptable adverse consequences. We've really got to be sure, and the modeling of the climate is pretty important. But that's kind of, I'm not going to say that's the easy bit, but that's the bit which has been given quite a lot of attention over the years up until now. The bit that gets more difficult is this the sort of cloud physics bit, where we've got salt particles which already they're lashed up by winds out in the sea, and there are waves, and the spray produces tiny droplets. Those droplets evaporate, the water evaporates, leaving salt particles, and they make their way up. These cloud concentration nuclei make their way up, and they help to create the clouds that we see. But it's all very turbulent. It's all very complex. So that is an area of modeling which Centre for Climate Repair is involved with as well, and how we do that modelling is pretty important. We've got to make sure that we don't just generate droplets and particles that in the end don't end up making new clouds. But the thing that's really exercising our minds at the moment is how we generate the spray. Now, one thing that I think is quite almost amusing is that the fossil fuel world is generating droplets, tiny droplets of diesel fuel and of other fuel to go into engines to create the power that we demand. They know a lot about droplets. And so that's the other thing that we've got here in Cambridge, is we do have a large research base on optimizing the performance of engines. And I think it's really significant that we can take up this baton from the people working in droplets for diesel engines and start looking at using the same technologies for droplets to produce whiter clouds. Now, the graph on the left shows you a typical example of the kind of droplet diameters that are being talked about for diesel engines, and they're measured in tens of microns. So we've got to bear in mind that we've got to be thinking perhaps of different technologies, different ideas for generating droplets, and that's really interesting, something that interests me very much. But the way that these droplets are produced goes back to Lord Rayleigh back in 1878, when he was looking at how droplets break up. You have a stream of water or whatever liquid it might be, and there's an instability which produces droplets. One of the key things which we're interested in is that if we're going to produce 800 nanometer droplet sizes, we've got to try and make sure that that droplet distribution, size distribution, is uniform. We don't want to find that, yes, we're aiming for 800 nanometers, but we get anything from 200 up to 5,000, because that's not good enough. Because what then happens is those droplets, the water evaporates to give us those really ideal 200 nanometer salt particles. So then we start looking at the droplet generators that we can just get off the shelf. It'd be great if we could use the kind, well, we all know if you're spraying your garden with something, or if you're got a spray paint you want to top up to touch up the paint on your car. Now, there's all sorts of nozzles out there, but if you start again to look at the droplet size from these nozzles, you're really pushing it to get droplet sizes down below 4 microns. So then we start thinking, oh, well, what about the inkjet industry? You know, inkjet printing. There's one sitting on my desk here as I speak, and it's absolutely amazing what has been done to make inkjets, these droplets of ink, just function perfectly well. Everyone's got one of these things on their desk. But again, if you look at the diameters, these droplet diameters are tens of microns again. But the one thing we've got to remember is the way that these are generated. It's done using microelectronics, silicon substrate with vibrating components to and warming the liquid up and so on to produce droplets of just the right size. So what we are currently engaging in right now is to take designs that Stephen Salter has prepared already in Edinburgh, and to build them and to optimize them to see if we can get these 800 nanometer droplet distribution that we need. Now, just to sum up then the things that we're looking at: climate modeling, where, when, how much cloud brightening do we need? It's all very well to know all that, but as has been mentioned before, you can't just wander in and start brightening clouds without really full and proper engagement with local communities and full and proper public involvement. One of the things I learned from the SPICE project that's our stratospheric particle injection for climate engineering, is that even if you want to do a relatively, what you might think of as a benign experiment, you discover that there's no such thing as a benign experiment when it comes to this kind of stuff we're talking about. We had a really good session right at the beginning of this summer series on the ethics and governance of marine cloud, ethics and governance of carbon dioxide removal. And you might think that carbon dioxide removal is kind of a no-brainer, you know, why, let's just do it. But it's not entirely clear that it has, that it's without ethical and governmental impact. So the technical things, droplet generation, what is the right size? There seems to be consensus, more or less, that we're aiming for 200 nanometer cloud condensation nuclei, but the research is not conclusive there. There are people who are saying, oh, we should go smaller, and others we should say it's easier to go bigger. We've really got to be sure that we're going down the right direction. And then how do we make those droplets and of uniform size, and these eye-watering numbers, 10 to the 17 droplets per second, can we do it? Scaling it up is the hard bit. Now, producing these 200 nanometer cloud condensation nuclei, lofting them into clouds, looking at the residence times, looking at the cloud physics. Now, all of this is fabulous, but we're not one-tracked on this, because there are other ideas that perhaps instead of producing these nano-sized salt particles by evaporating water from seawater, can we do direct dusting of dry particles? And there's a lot of thought that this is a natural process in itself, with dust blowing off the land over the sea, producing condensation nuclei that way too. So apologies that this hasn't been a particularly enlightening presentation, but I'm very pleased to have been involved today, and thank you very much for listening.
And thank you very much, Hugh. And I do have a clarifying question for you from somebody you know well, and I know well, Jamie Arnell. He's asking, does the salt precipitate out and contaminate ice or land with salt?
So yes, of course, the salt eventually comes down as rain. But we're looking at a 50% increase of cloud condensation nuclei in those areas where clouds are most likely to form. So this is, and in any case, the intention is this is done over sea, so hence marine cloud brightening. So yes, the salt will come back down again into the sea where it originally came from. There would certainly be questions to be asked if this salty air were to be blown over land, and of course we'd need to be very careful about that. But I think the short answer is it comes back into the sea, which is not especially problematic.
Well, thank you very much, Hugh. I'm now going to call on the three local members who are available to us for the general discussion, and ask some more questions that are firing in, and they are being selected out for me. So I'm just going to read a few. I've got, first of all, maybe this is a start for Alan, but anyone is welcome to answer. Can you explain to everyday people, apparently we are all everyday people, aren't we, what's happening to the Arctic? Would it be true to say that the Arctic and the Antarctic act as refrigerators to the world, and that carbon emissions are defrosting them?
Hello, it's Alan here. First of all, if you look at I know we're diverting a little bit. If you look at the planet another planet in our system, Mars, you find that the polar ice caps actually melt and transfer to the other side of the globe. So yes, these these polar masses are actually huge, effectively refrigerators, storage refrigerators, and they store a lot of liquid water, and therefore you can regard them as ways of keeping the planet cool. And the interesting fact, the scientific factor, is that the planet absorbs solar radiation and emits it to space. And in the equator regions, it absorbs a lot of incoming solar radiation. And in the polar regions, it emits it back out to space. So it is, in fact, yes, a giant refrigerator. But if I may, can I just comment on the question about salt that Hugh was asked? In fact, the amount of sea salt we're putting up into the marine cloud brightening is less than one good Atlantic storm. A good Atlantic storm in the winter will throw up all far more than we can do in a year. So yes, I hope that answers both questions.
Thank you very much. And I've got another question from Faye, which is, for these techniques to give a short-term solution to climate change, who is responsible? Actually, this question could be for me as well, for financing the technology and for its implementation. Who is responsible? Let's rephrase that perhaps as, who is going to?
Well, can I perhaps just say first that research needs to be done, and research is relatively cheap. And it's disappointing that research seems to be quite difficult to do and quite difficult to get funded, because I think of the questions about who ultimately will be paying for implementation if ever we do it, and who ultimately have their hands on the thermostat and who ultimately will be in control. It's a shame that we can't get on with the research while at the same time coming up with an answer to the question that's just being asked.
I'm going to suggest that the answer would be all of those who are affected by these impacts. And surely, if we are looking, for example, at sea level rise, as ice on Greenland melts, as ice in the Antarctic melts, etc., then we all benefit, and we are represented by our governments. I would have hoped that our governments would step in and fund the bigger effort required. There are, of course, philanthropic bodies that can take us quite a long way as well. But I think that was a pretty important question.
So, Daniel, is the Australian government interested in helping to pay for the restoration of the Barrier Reef?
Yeah, I'm happy to talk about our funding. So our funding for our work has been a mix of philanthropy and government funding. Some of the government funding competitive. So the first experimentation we were able to do out on the reef was through a jointly funded competitive call for interventions to help coral abundance on the reef, which was funded jointly by the Queensland and federal governments. And the Reef Restoration and Adaptation Program is funded through by the Great Barrier Reef Foundation, largely using funds from a large government grant that was made to that foundation, as well as attracting additional philanthropy. So a mixture of government and philanthropic funding.
Can I comment as well? I received some funding to do the work via securities grants from Bill Gates, and he funded it. But in my quotations, I usually say, if you gave me Harry Kane's salary for 5 years, or Rooney as it was then, we could fund all the research in the country. And if you gave me 1% or 0.1% of all the funding for COVID, we could set up a system.
Good. Let me just go to what I think is another good question. How can MCB, Marine Cloud Brightening Interventions Planning, take into account interannual variability, unprecedented changes in wind direction, or perhaps in a heat dome effect in Australia, but also more particularly in the Arctic. So this is directed again at all three of you.
Can I start with that then? A very quick comment. If you look at marine stratocumulus clouds under the three areas we mentioned, there is actually very little change in the dynamics and the structure of the meteorology in those regions. It's in when you've got the meandering jet stream in the northern hemisphere. In the southern hemisphere, you don't. That's the big difference between northern hemisphere and southern hemisphere. There are big local differences, but if you just chose those, and I'm not saying you should just change all the regions off Australia, there isn't actually that much difference in the local meteorological conditions as the planet warms up.
And
I think it's quite similar for the reef. During the bleaching season, the meteorology of the reef is dominated by trade winds coming from the southeast, but you do have periods where the winds switch westerly. They're normally quite brief, and so during those periods that are fairly brief, the wind actually then brings aerosols, natural aerosols, rather than cloud brightening sea salt from the land, and so the cloud brightening would become less effective in those times. So it's really, from an engineering point of view, it's an optimization problem. If you wanted to be the very most cost-effective implementation that you could, yes, you'd need to somehow understand what the meteorology was going to do in advance, which of course weather forecasting gives us the ability to do with some degree of accuracy. But beyond that, it's really your effectiveness might go down. If the wind's blowing in the wrong direction from where you've sited your stations, then you might be cooling water further out into the Pacific rather than directly over the reef. But that would still have some benefit, as some of the modeling showed. If you're actually cooling the water before it gets to the reef, it helps you to protect more of the reef than if you only start as soon as the water hits the reef.
Okay, I think we've covered that one. And the next one is this is from Sonia Galami. What negative environmental effects might marine cloud brightening in the Arctic have? What are we watching out for with these initial experiments as we perform them?
One of the things that we know from climate modeling, global climate modeling, is that there are knock-on impacts elsewhere on the planet. So if we change the temperatures, let's say in one region on the planet, we can expect there to be impacts elsewhere, and the impacts will not just be on temperature, but they'll also be on rainfall. And it's very important that we don't accidentally create a drought or a flood somewhere else. But of course, we've got to be mindful of the fact that if we don't do anything at all, we're going to have some pretty severe weather and climate impacts over the next few decades. So we've got a balancing act to do. Yes, if we do some marine cloud brightening and there are some adverse effects, how much adverse effect are we willing to accept, given that what we're doing is reducing the overall negative impact of climate change?
Can I comment on that as well? If you look at the Clausius-Clapeyron equation, you'll find that precipitation will increase over the globe as you warm it up. So that's one thing. But in my talk, there was a hidden slide which showed the effect on the models of precipitation globally. And you can actually see that the effect of doing nothing means that there's huge, bigger variations in precipitation over different parts of the world than if you do perhaps double CO2 and marine cloud brightening. So the change, though I don't have reluctance to believe numerical models at the climate scale, even though I spend my life looking at them, there is evidence to suggest that it actually reduces it. But one of the frightening things was that all the climate models I've looked at, there is a reduction. As you increase CO2, there is a reduction in rainfall in places like Arizona and Western USA. And with the increasing number of fires there, I don't want to believe the numerical models, climate models, but all the numerical models, climate models I've seen, there's been a reduction in precipitation in the regions that are now suffering forest fires. So there's going to be knock-on effects, and that's why we want to do the coded manipulation. But the evidence suggests the knock-on effects are less than doing nothing.
Thank you very much. There's a group of questions, and they've been partially answered, about the particle size. So in marine cloud brightening work, I think Hugh in particular has focused around a narrow particle size distribution for the sodium chloride crystals, peaking at about 800 nanometers. And so the question is, to both the Arctic work and the work down in Australia, what is the reason for selecting a particular particle size?
Well, so Alan had a slide, I think, which showed that why the 200 nanometer salt particle was optimal. But I think it's a really good question, because the 200 nanometer salt particle size may be optimal, but if it can't be achieved for some reason at sufficient scale, then maybe we have to be looking around at other sizes. But I think probably Daniel and Alan would agree that it's quite a good size to be aiming for right now. But it's a good question about whether it's the holy grail, or maybe there are some other optima out there that we don't quite know about yet.
I can comment a little bit in the Australian context. I'm sure Alan will have plenty to say too. One thing that makes that size particularly attractive in the, well, there's two things actually that make that size particularly attractive in the Australian context. One is that with the typical relative humidities that exist over the reef during summer, that the hydroscopic growth means that a 200 nanometer sized salt crystal will typically result in a sort of dropleted equilibrium size of around 400 nanometers diameter. And so that's about half of the size that you'd spray it out at. And it so happens that that size is optimal for me scattering. So for optimizing the direct scattering effect of those aerosols floating around in the atmosphere, the ones that aren't actually contributing to cloud condensation nuclei, or perhaps are floating around when clouds are not present, when the conditions for clouds are not right, are not ideal, then they're also making their optimum contribution if they're that size. I think the size of 200 nanometers it's been selected because it's right in that gap, and so it's a particularly conducive size to forming a cloud droplet under a wider range of cloud conditions. So if you start to move away from that optimum, it's not that you can't necessarily form a cloud droplet, but particularly as you move smaller, a decreasing fraction of those aerosols will activate to form cloud condensation nuclei. And I think this is primarily where the discrepancy comes in between some of the work. Some of this recent work out of the States is looking at particular cloud types, and I think the argument, there's a few, the energy may also go up the larger the droplet size you produce, so that's part of it. But the other part of it is that as you decrease the size of the droplets, it becomes harder for them to activate, and a smaller proportion activate. But if that means that you can more easily produce more of them, if the amount that you can produce goes up quicker than their activation goes down, then the optimum, it becomes an optimization problem, right? And the optimum may not be at the ideal size for producing cloud droplets.
I would agree with Daniel there. The growth rate of droplets is inversely proportional to the radius. So the smaller they are, the faster they grow. So that's the first thing. The second thing that always worries me is engineers talk about diameter, and microphysicists talk about radius, and then you have wet size, which is twice as big as dry size. So I always worry about what actually we're talking about in terms of that. The optimal size, I think, from a microphysicist is actually depends on the environment you're in. So when I said geographic, I don't mean geographic. I mean the water vapor, the mixing ratio content of the local region you are. Feingold, who was an American, also a very experienced cloud physicist, he chose somewhere between 200 and 800 nanometers, and you've got to work out the size. So yes, temperature and water vapor are critical, and the background number of aerosol, as I showed on that plot. If there's a very low aerosol content, and so as long as it's not too big, like a micron, almost anything will do to do it. But there's not many of those cases where you get stratocumulus clouds with low, very, very low aerosol count. So it's a I still think we're in the right ballpark. I think it will work if we stick in this ballpark, but I think we could optimize it more to make it more efficient. Yes.
Thank you very much. I'm going to.
I think it's possibly worth just noting, just because we're here and now, that the particle size we're talking about is almost exactly the same as the coronavirus size. So that just puts it into context.
Let's leave it at that, shall we? So let me move on. The question is really stimulated by Nisar Chatter, but we know there's a very recent United Nations Environmental Programme report on the dramatic impact on human beings as the Himalayan ice is lost and rivers dry up, which are major feed channels for very large populations in that area. Is there any SRM technique or SRM-like technique that could be used in refreezing glaciers like the Himalayas? There's a long.
Well, I think it's worth saying that the Himalayan glacier issue would have virtually zero impact on sea level rise, but a huge impact to the people who live in those regions. So when it comes to looking at SRM, solar radiation management, to deal with global climate, we've got to think about what impacts these techniques will have on different people affected by climate change. So what will be the effects on agriculture in, let's say, in California, and what will be the effect of flooding in Bangladesh, and what will be the effect of sea level rise in the Maldives? But then the question of what are the ongoing impacts on water supply on the Indian subcontinent? Right. I mean, it is a huge concern, and I don't think marine cloud brightening would have too big an impact directly on the Himalayan glaciers.
Can I comment on that, Hugh? I think you've hit the nail on that. I went to India to do some research project, and about 80% of the water supply for India comes from not from the glaciers, but from the monsoon. However, if you look to the north of the glaciers, like China, for example, then the control of the glaciers becomes far more important because water goes to China. So there's geopolitical things there. The other point about the marine cloud brightening, if you apply marine cloud brightening anywhere in the subtropics, you are reducing the flow of heat from the equator to the pole. That is the physics of what's going on. You might affect, sorry, Daniel, you might affect the your regions, but the result is you're cooling down the equator, and so in this transport. So as soon as you do that, the atmosphere is a global system. You will affect directly, well, not directly in that sense, because the atmospheric system will stop pumping all this heat towards the pole, and you find the effects all over the planet, not just what Daniels is doing. is not just affecting its coral reef, but it's actually saving us as well.
But the timescales are significant in that, marine cloud brightening cools the in mid latitudes, has a cooling effect, which has a cooling effect on the Arctic, which has there's a cooling effect on the planet. My worry is that we lose the Himalayan glaciers before those cooling effects really have kicked in.
I would agree with that, Hugh.
Okay, so let's move on. It's becoming a little bit too challenging right now. We'll come back to all these problems. From Rafe Pomerantz, how quickly could an MCB program, and you'll see this is directed at you, Dan, be initiated over the GBR? If you were to look at the whole GBR and you wanted to run a full-scale project, how long would it take you, regardless of finance requirements?
There's no easy answer to that question, because part of the answer is how desperate do you become to do it, I think. If you sort of extend current progress out, there's a very long way to go. The droplet size that we're producing with the nozzles we have is, as we just talked about, we don't think ideal, and it's a little bit of anyone's guess until we think that we're likely to get a positive effect with a little bit of improvement of the nozzles, but is that going to be enough? Will it give us the result of in the cloud microphysics that we want? We're fairly confident of getting that result if we have the perfect droplet size. We're a lot less confident if we try without the perfect droplet size, and how it'd be anyone's guess. But in terms of, let's say that we were proceeding with the technology that we have now, I think you're still looking at something like 10 years of R&D to understand the process sufficiently well, and to refine the sort of the science to practice well enough to be trying to do even the smallest meaningful portion of the reef, which might be a quarter of it or so. Hugh gave a great talk on how difficult it is to scale up. I think it's worth pointing out that that it's very easy to consider cloud brightening on these large scales using models or using theory, but the challenges of actually getting the engineering from where it is now to there is immense. I'm not 100% confident that we can even scale it up large enough to be effective for the reef, let alone areas much larger than the reef. When you actually look into the numbers and you look at the amount of energy and the amount of droplets we can produce now, and the efficiencies of how many you lose before they get to cloud height, and you start to add all of those things up, there's quite significant improvement. But that's not to say by any stretch it's impossible. There's been very little effort applied to this problem in reality until recently, and there still is very little effort globally.
Thank you very much. Very good reply. So I've got a question in again from Jamie Arnell. It seems counterintuitive that on the one hand, the salt quantities needed are similar to one big winter storm, and yet on the other hand, this approach would have a material effect on ice in the Arctic region. Is it likely that natural increases in storm activity with warming will do what we're envisaging without our intervention?
The answer is no, because the aerosol is in the wrong place. You've got to transfer that aerosol, those particles. We did the experiment of flying in the vocals, and you were flying underneath the clouds, and the results came over the tower naught. And I said, that's impossible. There is no way you can have zero. And we found over hundreds of miles, well, periodically, that there was no aerosol there. The air was pristinely clean. And that is like that every day of the year in those regions. Yet you go to the Northern Atlantic under a storm, then the aerosol level you just can't see because there's so much aerosol there. So I'm afraid these regions are, it's like a high pressure. You've got high pressure causing a heat wave, and there is complete difference from maybe 500,000 kilometers off to the west, where there is a storm going through or a frontal system. The atmosphere is very segmented in many ways. So yes, I'm afraid that's the way. Under stratocumulus clouds, that is the place to put the aerosol, and that is where it has most effect. And other than injecting it there, there's no other way of getting the aerosol there.
I've got dozens of questions flying in, but looking at the time, I fear that I'm not going to be able to put any of them to you. So let me simply say, first of all, a very big thank you to the four speakers. Let's not forget that Leslie's contribution was also very interesting. And really very, very stimulating. What we are talking about in refreezing the Arctic is the need to buy time. I think we've just got to remember that the overall project is only going to be managed if we reduce emissions deeply and rapidly, and if we bring greenhouse gas levels down to a level where these things are no longer threatening us. And our belief in the Centre for Climate Repair at Cambridge is that we have to do greenhouse gas removals at scale to bring levels down from the current over 500 parts per million, please, counting in methane properly, to something like 350 parts per million CO2 equivalent. We're not going to manage that before the end of the century. That's why we have to buy time now. So deep and rapid emissions reduction, and even working as fast as we can on greenhouse gas removal, we need to buy time while those are managed. And this is why we have to talk about refreezing the Arctic, about saving the Great Barrier Reef, and about a series of other projects that really are already showing that we're passing the tipping point now. So I just want to say that the objects of the Climate Repair Centre here at Cambridge have been delivered through the series of workshops, and there are a number of people to thank in developing these workshops. First of all, Hugh Wood himself, Hugh Hunt himself. Where did I find that word wood from? Hugh, our Deputy Director, has been heavily involved in leading the development of these projects. He's had a lot of help from Rafe Pomerantz, so a big thank you to Rafe, and from Dan Badansky, the big international lawyer in climate change, who's just coming to the end of yet another stay here in Cambridge with us. I think I would also like to thank Stephen Salter, who has contributed heavily to all of our thinking on marine cloud brightening. And we are working closely with Stephen and his team at the University of Edinburgh. But also now let me emphasize the importance of methane. The rise in methane that has happened more recently than the rise in carbon dioxide is now heavily with us. And it has reached the point that if we count methane against carbon dioxide at what I would call a proper level, 140 times the impact per molecule in terms of its dynamic effect of the temperature rise it would cause today, it means that methane is as important today as carbon dioxide in terms of its increase on global warming, its increased impact on global warming. So we are now planning a next event in September, which will be focused on methane removal. So here in Cambridge, we're keen to work with universities around the world, with governments around the world, with public and private sector companies around the world, because we need to do this globally at a global scale to manage what is the biggest challenge our civilization has ever had to face up to. So thank you to all of the contributors to this series, and I look forward to working with all of you as we move forward in time. Just before I leave you, we have our artist, Tom Mclean, who's been busy doing sketches and whatever. and I'll ask Tom to put his sketch, which is a brief abstract of what you guys have been saying during this afternoon. So here is his sketch. Tom, thank you very much. And yes, he's enlarging it so we can read it in a bit more detail. It's a wonderful pictorial summary of what we've been hearing about today, just to remind us all. So can I thank also the staff who've been here abundantly helping us, Katie Price, Antoinette, who's both of them sitting here with me in our office in Downing College. We have relied heavily on the staff for all of the backup they've provided. Thank you very much.